Hello, everybody, and sorry for the 3 minutes delay today. I was running late because today we're having a bad weather over here. Hello, everybody. Oops, and I can't hear my voice, so let me mute the other microphone so you guys don't hear that noisy echo. All right, cool. So let me just fix something before we start. Just like that, that's better. And I'm gonna prepare my notes. And voila, it's time to start. Okay, so I hope you guys enjoyed your weekend and your day so far. We have a rainy day, but we have this meetup. So I hope you guys will have some fun and will learn something new. And if not, maybe we'll refresh some info you had already. And let's start our presentation for today. So today we are going to continue the same topic that we started 2 weeks ago, which is about evolutionary robotics. Last meetup, that's even better and easier. We reviewed 2 papers. The first paper was written by Professor Hod Lipson, and the second paper was written by Nolfi and Floreno. And today we're gonna continue. But before we start, again, I want to hear from you all. So please, if you have any research projects, any cool ideas, feel free to reach out and share them with me, because we want to do this together. Let's go. As I mentioned earlier, today we're going to finish the paper that we started last week, which is Evolutionary Robotics Tutorial by Nolfi and Floreno. But before we dive into their paper, I'm going to introduce the topic, which is evolutionary robotics, which is as simple as using evolutionary algorithms to automate the creation process of robotics, to be specific, autonomous robots. And this method is inspired by the Darwinian principle of selective reproduction of the fittest. So next, we have the tutorial. The next slides were made by Nolfi and Floreno. So I decided to use their slides because they did a great job in the graphs and the design. So why should I start all over again? I mean, I have something great, so I'm gonna just use whatever they did in order to discuss this topic. So last week, we stopped at this slide, which is evolution in simulation. And we talked about the reality gap, because most of the time, researchers will make robots or implement robots in simulation, and then they will try to evolve these robots in simulation, and they will work fine. But then when they will try implementing physical robots, they will have some issues, which is known as the reality gap. But in this presentation today, we're not gonna discuss reality gap, but we will start talking about evolution in simulation. So to accurately model robot environment interaction, you will face some problems. The first problem happens because the different sensors and actuators of a robot, even if these sensors and actuators are identical, they will produce different results. Why? Because of slight differences in their electronics or mechanics. So in these 2 graphs that we can see in the slide, we have the same infrared sensors of a single chimera. If you look at the 2 graphs, you can easily notice the difference the difference between the infrared sensor readings when exposed to the same external stimulus. These graphs display the activation state of two sensors of a single chimera placed at different angles and distances with respect to a cylindrical obstacle. As you can see, the second sensor is sensitive within angle and distance ranges that are nearly twice as large as those of the first sensor. This also implies that two different robots may perform very differently in identical conditions because of the differences in the sensory characteristics. Interesting. I'm not going to complain about my robot's behavior from now on. Designing the fitness function. The fitness functions usually include variables and constraints that rate the performance or the expected behavior of the robot. But these variables and constraints are difficult to choose because the behavior evolved by the robot is not fully known in advance. For these reasons, designing effective fitness function is a difficult task and often require a trial and error process. So you can see here we have three dimensions. We have functional behavioral, we have explicit implicit, and we have external internal. This is the external internal, functional behavioral, and explicit implicit. So the first one, which is functional behavioral dimension, indicates whether the fitness function take into account specific functioning modes of the controller or the behavior of the individual, which is the individual robot. For example, in evolving a walk behavior, a functional fitness function will rate the oscillation frequency of the legs, while a behavioral fitness function will rate the distance covered by the robot. Okay? Now we'll talk about the other dimension, which is explicit implicit, or the Y dimension. This defines the amount of variables and constraints included in the function. For example, an implicit function would select only robots that do not run out of energy. Instead, an explicit function would include variables and constraints that evaluate various components of the desired behavior, such as whether the robot approaches an energy supply area, the travel velocity, the distance from obstacles, and so on. So the third dimension, which is external internal, or the Z dimension, as you can see here, the Z axis, indicates whether the variables and constraints included in the fitness function are computed using information available to the evolving agent. An example of external fitness function, for example, might take into account the distance between the robot and its goal. That is an external variable because it cannot be computed using the information coming from the sensors of the robot. In addition to specify a fitness function, we have to decide how to encode the robot control system and eventually the robot body in the genotype in a manner suitable for the application of genetic operators. Oops, I just got a comment, probably about the previous slide. Oh, Stefan. Hi, Stefan. Stefan says that he likes that the same electronics will have different sensors readings, just like our senses in nature. You're absolutely right. Like, we have two eyes. One of them might be stronger than the other. One of them might be weaker. Two ears. Some people are sensitive for one ear more than the other. So yeah, you're absolutely right. So back to genetic encoding. In most cases, the phenotypical characteristics subjected to evolution are encoded in a uniform manner so that the description of an individual at the level of the genotype assumes the form of a string of identical elements. Could be binary numbers. The transformation of the genotype into a fully formed robot is called the genotype to phenotype mapping. A good genetic encoding should exhibit several properties. Number one, evolveability, expressive power, compactness, and finally, simplicity. What is evolveability? It is the ability to produce improvements through the application of genetic operators. This is obviously a very important criteria. The second requirement, which is expressive power, is the possibility to encode many different phenotypical characteristics, such as the architecture of the controller, the morphology of the robot, the rules that control the plasticity of the individual, excuse me, and eventually the rules that determine the genotype to phenotype process itself. Number three, compactness. The length of the genotype can affect the dimensionality of the space to be searched by the genetic algorithm that, along with the characteristics of the fitness surface, may affect the result of the evolutionary process. And finally, simplicity. So obvious. I can't say more. Simplicity is simplicity. So, adaptation. As the title of the slide says, adaptation is more powerful than decomposition and integration. The main strategy followed to develop mobile robots has been that of divide and conquer, which is dividing the problem into a list of hopefully simpler subproblems, then building a set of modules or layers able to solve each subproblem, and finally integrate the modules so to solve the whole problem. Classical approaches to robotics have often assumed a primary breakdown into perception, planning, and action. However, this way of dividing the problem has produced limited results, and several researchers following Brooks considered such a division inappropriate. For these reasons, Brooks proposed a radically different approach in which the division is accomplished at the level of behavior. The desired behavior is broken down into a set of simpler behaviors which are activated or suppressed through a coordination mechanism. This approach has proven to be more successful. I can see it can be more successful because when you're dealing with robots in general, it is different than dealing with any algorithmic problem that we usually use divide and conquer to solve it. But in general, this method, the new method, leaves the decision of how to break the desired behavior down into simple behaviors to the designer, which is not clear how a desired behavior should be broken down, whatever. should be split into simpler behaviors or simpler subproblems. All right. Proximal and distal descriptions of behavior. The main reason for which it is difficult to break down a desired behavior into simpler pieces is that behavior is not only the result of the robot's control system, but the result of the interaction between the robot and the environment. To better understand this point, it is useful to distinguish two ways of describing behavior. You can either use the distal description of behavior or the proximal description of behavior. This is the distal description, and this is the proximal description. The distal description of a behavior is a description from the observer's point of view, in which high-level terms such as approach or discriminate are used to describe the result of a sequence of sensory motor loops. The proximal description of behavior is a description from the point of view of the agent's sensory motor system that describes how the agent reacts in different sensory situations. It should be noted that behavior from the point of view of a distal description, for example, exploration behavior, is the result not only of the behavior from a proximal description point of view, but also of the environment. That's why we always consider the robot environment interaction. Modularity. That's my favorite subject. So in this slide, we will discuss the relation between robotic behaviors and modularity. From the point of view of the decomposition and integration approach, the use of modularity is implicit in the approach itself. The desired behavior is broken down into a set of basic behaviors, such as approach or avoid, which correspond to a set of subcomponents or modules of the controller. Conversely, in the case of the evolutionary approach, the use of modularity is not mandatory, as we described earlier when using mobile robots. That produce the behavior that can be decomposed into a set of basic behaviors. So in this slide, we have some questions. Is modularity useful in evolutionary robotics? And what is the relation between self-organized neural modules and behaviors? To answer these questions, the authors presented some experiments. Unfortunately, they are not covered in this presentation, but you always can go and check the research for a series of experiments, including garbage collection experiments, where they made in an attempt to answer these questions. Evolving complex behaviors. So we have a bootstrap problem, which is selecting individuals directly for their ability to solve a task only works for simple tasks, of course. And again, we should not forget using fitness functions. incremental evolution, starting with a simplified version of the task and then progressively increasing complexity, including in the selection criterion, also a reward for subcomponents of the desired behavior. You can always start with a simplified version of the task and then progressively increase its complexity by modifying the selection criterion. Next, we have a technique that has been used by many researchers who studied the evolution of visually guided robots. In these experiments done by those researchers, they trained a specially designed robot called gantry robot. I don't know if you guys heard of it. To be honest with you, I've never heard of it. So they trained this gantry robot to visually discriminate between a triangular and a rectangular white shapes on a black background. The evolutionary process consisted of 3 stages of increasing complexity. First stage, one full wall was covered with white paper, and the robot was asked to move forward the wall. In the second stage, the white target surface was restricted to a 22 centimeters wide band. And finally, in the third stage, the white paper was substituted by 2 white shapes, a rectangle and a triangle. And the robot was asked to move forward the triangle. Although these techniques might solve the bootstrap problem we mentioned earlier, they required that the designer identify the right stepping stones necessary to obtain a given behavior. For the reasons we mentioned earlier, this might be a hard task. Let me check the chat. Oh, cool. So Stefan knows the robot that we're talking about. Excellent. So Stefan mentioned that this robot is probably in one of his robotics behavior books on the shelf. Can you share these books with us, please? Because unfortunately, I've never heard of it before reading this paper. And Stefan also had a comment. I think it's about probably the first slide, the previous slide. Stefan mentioned that he finds interesting the similarities and differences between behavior implementation in evolved mobile robots, exactly, and not just human, but other animals too, with various levels of complexity in their behavior. Yes, you're absolutely right. And I see in some new researchers, it's not new actually, it has been done for a long time, they are trying to simulate some animals' behavior or animals' cognition and try to copy these processes to robots. But yeah, I like comparative studies in general. I think they need to focus on comparative studies in order just to study, the cognition of a certain animal or a certain creature, and then try to implement robotic behavior that is similar to that. So yeah, that's a good call. We need to do something about it. Thank you. Thank you for your cool comments and for trying to find that book for us. So now we're going to talk about learning and evolution. Just go back. Okay, cool. So how learning and evolution interacts. There are different timescales, different mechanisms, and of course, similar effects. So what are the learning advantages in evolution? Adapt to changes that occur faster than a generation, of course. extract information that might channel the course of evolution, help and guide evolution, reduce genetic complexity, and increase population diversity. But on the other hand, what are the costs of learning and evolution? Of course, the biggest one is the delay in the ability to achieve fit behaviors, increased unreliability, or learning wrong things, physical damages, energy waste, and tutoring. Well, I might agree on energy waste, but physical damages, I don't think so. So let's see evolutionary reinforcement learning. Evolving both the action and evaluation connection strength. Action modules modifies weights during lifetime using techniques such as CRBP. And they validated this method, which is the evolutionary reinforcement learning, on mobile robots. So in this slide, they didn't mention a lot of details about evolutionary reinforcement learning, but in one of our next meetings, might be next week, might be the week after, we're going to discuss evolving artificial neural networks. And we're going to discuss evolutionary reinforcement learning in more depth. Because I mean, I like what they mentioned in this slide, but I feel like we can add a lot to this area. Let's move on to evolutionary auto-teaching. All weights genetically encoded, but one half teaches the other half using delta rule. And individuals in this case can live in one of two environments, randomly determined at birth. Learning individuals adapt strategy to environment and display higher fitness. Okay, interesting result. And you can see here in this graph, learning generation and no learning generation. Yeah. Learning showed better results than no learning. Cool. And Stefan agrees with the next topic, which is evolutionary neural networks. So yep, that's gonna be our next topic. I can't believe it. Summary. But that's not our conclusion. This is just to summarize the previous part, which I'm not gonna say compares, but let's say discusses learning and evolution. Instead of saying compares learning to evolution, nope, it discusses both of them. So learning is very useful for robotic evolution. It accelerates and boosts evolutionary performance. It can cope with fast-changing environments, and it can adapt to unpredictable sources of change. So in order to distinguish between learning and adaptation, we should know that adaptation does not necessarily develop and capitalize upon new skills and knowledge. And you should also know that learning is an incremental process whereby new skills and knowledge are gradually acquired and integrated. Next, we have competitive coevolution. Fitness of each population. It depends on fitness of opponent population. I wanted to ask you about some examples, but you can guys read it here. Predator prey and host parasite. It may increase adaptive power by producing an evolutionary arm race. Also, more complex solutions may incrementally emerge as each population tries to win over the opponent. Competitive coevolution might be a solution to the bootstrap problem. I don't know if you guys agree with that. Please feel free to use the chat window to share your opinions with us. The fitness function plays a less important role in this competitive coevolution. And finally, continuously changing fitness landscape may help to prevent stagnation in local minima. All right. So next we have coevolutionary pitfalls. Everything has pros and cons. So on the left side of the slide, you can see that the same set of solutions may be discovered over and over again. So this cycling behavior may end up in very simple solutions. The solution in this case is retain best individuals of last few generations. On the right side of the slide, which uses conventional evolution, the fitness landscape is static and fitness is monotonic function of progress. In the competitive coevolution, the fitness landscape can be modified by the competitor and fitness function is no longer an indicator of progress. Solution in this case could be master fitness or CIAL graphs. So we have here a comment about competition for fitness evaluation. Stefan mentioned that he doesn't see any downside to that. Yeah, I mean, yeah, it has benefits. The downsides are not comparable to the benefits that we could get from competition for fitness evaluation. So I kind of agree with you in this matter. 90%, no, more than 90% agreement. So here we have some examples of coevolutionary agents. You can see the ball catching agents in the top part. And in the second part, you can see a simulated predator-prey game. Yeah, we always agree, 90% agreements all the time. You're absolutely right. So after seeing some examples of coevolutionary agents, now we want to see coevolutionary robots. So here you can you see them? The two Kipera robots. So they are energetically autonomous. Again, predator-prey scenario. And it has time-based fitness. So the controllers in this case downloaded to increase reaction speed. And the last best 5 controllers were retained for testing individuals. To summarize this part about competitive coevolution, we want to say that competitive coevolution is challenging because the fitness landscape is continuously changing, and it is hard to monitor progress online. And the last reason is cycling local minima. So when environment is sufficiently complex, or Hall of Fame method is used, the system develops increasing more complex solutions. It can work and capitalize on very implicit internal and behavioral fitness functions by exploring a large range of behaviors triggered by opponents. When co-evolving adaptive mechanisms, prey resort to random actions, whereas predators adapt online to the prey strategy and report better performance. Next, we have, that's also my second favorite topic, which is evolvable hardware. Evolvable hardware could be evolution of electronic circuits or evolution of body morphologies, including sensors, of course. So why do we need to evolve hardware? Hardware choice constrains environmental interactions and the course of evolution. Evolved solutions can be more efficient than those designed by humans. Totally agree with that. Develop new adaptive materials with self-configuration and self-repair abilities. Yay! We talked about self-reconfiguration, self-repair, and self-assembly in our previous meetups. It's time to highlight them again and remembering them again. Evolutionary morphologies. In the top part of this slide, you can see evolution of Lego structures. You can see some bridges and cranes. It was extended to objects and robot bodies. You can use this link to see the demo. And I don't know what's going on the bottom part, which is an example of an evolved crane. But as you can see here, it's a black image. So probably it's a video that is not available in their slides. Maybe if you go to the paper, you can find a link to this video. So co-evolving morphologies. They referenced here evolved virtual creatures for Carl Sims. And yes, I like this paper a lot. I read it, I referenced it in my research before. It is a great paper. And they also referenced another research done by Komosinski and Olarowski. I'm sorry if I'm pronouncing the names wrong. In this study, they discussed the effect of doubling sensor range on body wheel side. No, actually, this is a third paper that they referenced by Lund and other researchers to study the effect of doubling sensor range on body wheel size. I mean, we discussed evolving morphologies in some of our previous meetups. We can go into more details in the next meetups if you guys would prefer that. So I'd like also to hear back from you in order to know which direction should we follow in our next meetups. So finally, we will see some suggestions for further research. Encoding and mapping of control systems, exploration of alternative building blocks. This is a good one. Integration of growth, learning, and maturation. Incremental and open-ended evolution. Also, this is another good topic. Morphology and sensory co-evolution. Application to large-scale circuits. User-directed evolution. And finally, comparison with other adaptive techniques. And these are some recommended readings by the authors, Nolfi and Floreno. You can just take a look at them. And if you have any questions, feel free to reach out and ask, whether here on YouTube or on the meetup group. And I can see another message in the chat from Stefan. Probably this was, I think, related to one of yeah, it was about coevolution. Oops, it's gone. Oh, it's here. There's a problem that outside influences might skew the results between two or more robots. I think, yes, Stefan was referencing probably this slide. Yeah, where he mentioned that coevolution, that outside influences might skew the results between two or more robots. Yes, you're absolutely right. And about the last slide, which is suggestions for further research, we have another suggestion, which is which researchers would take it? Evolving two robots that aren't completely the same, such as evolving a UGV alongside a UAV, so that they may learn to work better together. I like this idea. I like it very much. I've never done work similar to this before, but that's going to be great. Have you done something similar to that, Stefan, or just this is just a thought that you're thinking about? So again, to articulate this in a better way, so if you guys want to listen to this podcast or webcast later, so the idea was evolving side by side two robots that aren't completely the same, but they will learn to work better together. Wow, excellent. So you should present for us the results, or maybe questions that you're trying to tackle and answer. And we can together think about possible solutions or possible scenarios to testify this. And I'm not sure if you guys received my messages on the meetup group, but I sent a video last week about my latest research work, which is a robot that assembles another robot. I don't know if you guys took a look at this. If not, I might just add the link of this video below this video in the description field so you can take a look at it and tell me what do you think. Oops, so this meetup today took longer than usual. Now it's 3:46. And thanks for you guys if you watched the video. And thanks for you who are RSVP'd to just keep the link and watch it later. And have a wonderful rest of day. And I'm going to send the message very soon about next week. Yeah, we're going to meet next week, not the week after, because I'm going to be traveling overseas on the week of April 10th. So we will meet next week, next Monday, April 3rd, and then we're going to meet on April 17th, which is my birthday. So looking forward to meeting you next week and on April 17th. So have a wonderful rest of the day and see you guys soon. Bye-bye.